Alright, for those who are watching the recording, I got started without forgetting to record, and I'm just going through the table I made in last year's revision seminar, which is here on the webpage too, and I talked about the first order ones, and I put in what you did in Maths 1B, and then we've got the exact one which is new. Second order ones come in linear. This is in Maths 1B, the homogeneous versus non-homogeneous stuff with the characteristic equations. But you've learned some new methods in Eng Maths IIA for figuring out what this particular solution is. There's the method of undetermined coefficients, which is what you did in Maths 1B, and there's variation of parameters. And you've also learned a few technical details about undetermined coefficients for situations that you didn't see in Maths 1B. So that's where the new stuff is. And then this is the really new stuff in Eng Maths IIA, is that we've got the linear ones with variable coefficients. So instead of having like 3y double dash, we've got x squared y double dash. And they're either homogeneous, in which you can use sort of a power series sort of approach. And even in without it, it doesn't matter. And the Frobenius method is a power series approach as well. And so there's two sort of general power series approaches. To get the second solution from your homogeneous one, there's this thing called reduction of order. So that's a method for finding solutions to the homogeneous one. And then there's a way of figuring out the particular solution, which is variation of parameters. So you'll see there's all these methods that you've been told, and therefore figuring out certain bits. And knowing where in this thing the methods fit could be a bit helpful for knowing how things go. You have been told higher order ones, so like y triple dashed, and your approach that you've been taught to do that is that for linear higher order ones of constant coefficients is to convert them to a system of linear equations, or to use a characteristic equation, and it comes to the same thing in the end. So that's your ordinary differential equations, and that's already online. And then there's systems of ODEs, and we only consider the linear ones with constant coefficients so that we can turn it all into a fabulous matrix and use eigenvalues. I told you in Maths 1A they'd come back to haunt you, didn't I? So you can use eigenvalues to solve the systems of ODEs. I'm not talking about how to do this, I'm just talking about how it all fits together. And then where does that go? And then there's a couple of partial differential equations, which is this separation of variables that we were all worried about in the last assignment. And then there's Fourier series, where we rewrite our function as an infinite series of sines and or coses. And then if your function's periodic, then there's these Euler formulae for the ones where it's period 2 pi. And then for period 2L, you can convert. And if it's not periodic, you can extend it either oddly or evenly and send it back to be periodic again and use that version. So that's my understanding of what's in Eng Maths 2A for differential equations. And did I mention variation of parameters? Yes, I did. Okay. So whenever you're studying anything, it's a really good idea to get an overview of the whole thing yourself, and rather than trying to focus on any of the details, try and focus on the big picture of what goes where and how to decide what to do when. And if you learn a method with a name, knowing what the purpose of the method is for, so say this method is for this purpose, is easier than remembering the details of how it's done. You have to remember that too. But I find that knowing purposes is better. So that's just some advice for the future. Okay, so there you go. I thought I'd just do requests really, because if I can get enough people in the room at once, then you won't all be in the Maths Learning Centre, because you see roughly the amount of people here, you would fill the whole room. There wouldn't be any room for first years, and you know, past you would have been really annoyed if there were a whole lot of Eng Maths people kicking you out of the Maths Learning Centre when you were in Maths 1A. So On that note, when Barry does his consulting time in the Maths Learning Centre, I'm going to set up a space for you. I'm going to commandeer some tables in the space next door for you guys, so for him to do that. So don't, when he says he's in the Maths Learning Centre, he'll actually be just outside, just on the other side of those ropes. So I just thought I should warn you to not look for him inside, because I'll set him up at his own spot. Okay, so I've already had one request by email, which was to do something like the 2009 exam question 4B. So and I got Joshua to send me the exams so that I can actually look that up. So the library has decided not to provide past exams on their website anymore, which was nice, but except when a lecturer like me, who doesn't have access to engineering maths, therefore can't access past exams at all, except through the students. So thank you very much. So who was that? I've forgotten who, and are you here, who asked for that? Was that you that asked for that? No, someone else. Oh well, they're not here, so they can watch it on the recording. Right, so this is it here. Oh yes. Use the substitution x equals cos t to show that can be transformed to equation 6, which I presume is this equation. No. That equation. Okay. Hence write the general solution to 6 in terms of trig functions. Okay. All right. I might as well just... It occurs to me that that's different to the rest of the question, so I will do just part B separately. So let's see. We were given this equation. This is David thinking on the fly. You can see how it's done, right? Okay. So these are the two equations that are supposed to be transformed into each other. We have this equation. And we have this equation. And we're supposed to do a substitution of x equals cos t. Okay. So the person who emailed me said, could you do this? Because I don't understand Orms's solution. Has anyone read Orms's solution to this question? Have you got it with you?
I have it.
Okay. Oh, that's better. Really not doing well today. Did revision seminar for like 3.5 hours straight yesterday, and I was not well. All right, well, sometimes the solution just has to be done live in order to make sense. So let's see if we can make this work. So, just let me think this through. Currently this y is a function of x, right? And this y here is a function of t. So I need to somehow turn my dy on dx's into dy on dt's, or vice versa. They specifically in the question said that I'm supposed to turn this into that. So I'm hoping that I can go forwards Okay. Well, not sure yet. But I do know that the chain rule alright, so I'm going to need to convert this thing in terms of t into x because they've told me I'm supposed to go that way. So I need to figure out what dy and dt is in terms of dy and dx. So dy and dt, according to the chain rule, should be dy on dx times dx on dt. Now that's the chain rule as you would use it in, say, dynamics. This is the most useful version for the moment. And so I can convert my dy and dt into something involving dy and dx. But I don't have a dy on dt in this, so I'm going to need to do d squared y and dt squared. So that means I'm going to get what I've got here and differentiate it with respect to t. Okay, lovely. Now let's see if we can follow what they've done here. Oh, they've done straight to the chain rule for second derivatives. Yeah, I don't know how that works, so I'm just going to make it up. So this is a product, so I could use the product rule, right? So I should be able to go, well, this would be d on dt of dy on dx times dx on dt plus dy on dx times d on dt of dx on dt. I did the product rule there. That was from the product rule. Okay, so I did the derivative of that and kept that one as it is, and then I kept that one as and did the derivative of that. Okay, so d on dt of dx on dt would be d squared x on dt squared, because that's the derivative of the derivative, so that bit's good. And this bit here, d on dx of dy on dx, d on dt of dy on dx. Alright, I could use the chain rule for that as well. So this one I could do, just for this bit here, I could do d of this, dy on dx, d of that on dx times dx on dt. That's the chain rule. Okay, so just ignoring everything else, I've got d of crap on dt would be d of crap on dx times dx on dt. And then there's still a dx on dt here. And then this is d squared x on dt squared. And so I've got, well, d on dx of dy on dx is d squared y on dx squared. And that is dx on dt squared. And that's dy on dx times d squared x on dt squared. Pretty sure I've done that right. Okay, it's now markedly different from the one that the ORMS has. So I'm just going to see where I go from here. So presumably I should be able to sub that in there, which doesn't look happy, but we'll see what we get. So in order to make this work, I can figure out what dx on dt is because I was told what x was in terms of t, so I can figure them out. So x was cos t, so dx on dt would be minus sine t, and so d squared x on dt squared would be minus cos t, which means I can sub both of those into here. So d squared y on dt squared would therefore be d squared y on dx squared times dx on tt squared, which is cos t squared, plus dy on dx, and we've got d squared x on dt squared, so that's the minus cos t. Oh, And actually, you know what? I don't want t's in this at all, do I? Because this one that I'm aiming for doesn't have any t's, it's only got x's. So what I should really do is I should write this in terms of x. That'd be totally better, because cos t is actually x, so this would be d squared y on dx squared x squared plus dy on dx times minus x, because cos t is x. Okay? So just to make my life cleaner, this would be y double dash x squared, and this would be y dashed minus x. Yep? So now if I substitute that back into the other differential equation, so I did this into, let's call that 1, sub into number 1, sub into the differential equation. So my original differential equation was d squared y on dt squared plus alpha squared y equals 0. And I'm supposed to sub this into there. So I've got y double dashed x squared plus y dashed minus x plus alpha squared y equals 0. I've lost a 1. This is really close, but have I done something wrong somewhere? Can someone see where it is? Because this is supposed to be 1 minus x squared here.
David,
Yeah?
did you go up a bit? Yeah. Up a bit more. Yeah, it might be something to do with. When you substitute that equation, that line that says 1, and you put in dx by dt.
Oh, you're right, thank you.
Yeah.
This is sine t, isn't it? Yeah, awesome. Thank you. So, sine t squared, the minus will get squared, so it'll go away, so I'll get sine squared t. Okay? And so sine squared t would be 1 minus cos squared t. So, sine t squared would be 1 minus cos t squared, which would be 1 minus x squared. Yay! Thank you. And so I've got 1 minus x squared y double dashed minus x y dashed plus alpha squared y is 0, which is what I was aiming for. Awesome. Which is way simpler than what they did, as far as I can tell. Okay, so just to point out what happened to the Orms people, they did similar stuff to me. And then this is just like, whoa, crazy stuff. Yeah, all this crazy stuff here. Because what they've done is they've started from this one and gotten to here. And I did it the other way around. And I did it the other way around because that's specifically what the lecturer asked me to do. It said in the exam question to transform that this can be transformed into this. So the lecturer who wrote the exam is thinking that you should start here and end here, and they're given that suggestion because they think it's the easiest way. And so it's usually the best plan to follow exactly the instructions you're given, because it's often shorter. That's the learning skills moral. The other moral is this is how to do the chain rule twice on multiple derivatives. So that's the derivation of that. Okay. And the other moral is as well, do be careful that you sub stuff incorrectly. Okay. Did Barry actually talk about substitution much at all? No, can you talk about it? Yeah.
Really,
Okay, but it's in the course somewhere.
somewhere, yeah.
So it's not impossible that you could be okay. Just thought I'd check because 2009 is quite a while ago, so it might have lapsed from the course, but maybe not. Okay, so have I got any more requests?
Anything on power series?
Sorry?
Anything on power series?
Anything on power series? Yes, let's do it. Okay, so power series are a method for solving differential equations that you don't know how to solve any other way, and they're really useful for ones where you have, my understanding of it is it's really useful for ones where you have like a polynomial times like y double dash plus polynomial times y plus polynomial, plus y is 0, that sort of thing. And it should work okay even if it doesn't come out to a 0, I reckon. As long as it comes out to something like a polynomial, it should be okay as well. And the reason the polynomial thing works really well is because you're going to assume that y is a polynomial. Well, an infinite one, but that's the idea. So you're going to, this is just my understanding of how this works. So we're going to assume sort of y is a0 plus a1x plus a2x squared plus forever, which is polynomial-ish, which means if I multiply it by x, it'll still be an infinite series, and if I multiply it by x squared, it'll still be an infinite series, and so you'll be able to do infinite series. You'll be able to get a nice big infinite series that'll all collapse down into a single sum. Okay. And then there's the specific circumstances with the Frobenius method when you have to start higher up than this and you have to times it by x to the r. That's my understanding. Okay. But both of them, that Frobenius method, as far as I can tell, other than the x to the r thing and this indicial equation thing, it still runs by the same sort of reasoning. So, well, there's a problem here. They actually give you the recurrence relation, so I actually want to do one. So has anyone got an exam question that they've been thinking about that has a power series in it? Otherwise it'll take me a while to find it. There's one, 2009 question 4A has one, but they do the work for you. So I want to have a full example rather than so that you can see what they've done fits. Did you find one?
Oh, yeah. 2011 question 3 doesn't have a recurrence relationship.
Sorry, it does.
Doesn't.
Okay, but it expects you to use power series.
Yes.
All right, so let's do that. Second order differential equation. So it's second order ODE. It has polynomials for each of its coefficients, and so power series isn't such a bad plan. And it has equals 0. Okay. So this is a Frobenius method one, right? Yeah. So what does it mean to say regular singular point? I don't know off the top of my head. I'm sure it's important.
It means it's not analytical at, at p of x or q of x, which is like the functions, like the coefficients of y dash and y respectively.
Okay.
When you put it in general form.
Okay, so from the audience we've got, you put it in standard form by dividing by whatever's next to the y double dash, is that right?
Yeah.
And so you get these two functions that both have x's on the bottom, and you need sort of like the first, and they don't work, right? Because they've got x on the bottom, and so when x is 0, it's crazy. But if I multiply them by the appropriate powers of x, then they do become analytic, so it's okay. That's the idea behind it. Okay, you need to look up definition. I find it's really useful, especially in a course like this, is to run through the whole thing and write down all the terminology in one page, so that you can, and how to tell when it is and how to tell when it isn't and why you care. Okay, so apparently, because it's a regular singular point, the equation has at least one solution of that form. And they've done half of the work for you. Okay? So you'll notice in these exams they'll do part of the work for you. So what was this, 2011? Okay. Thanks, mate. No, he's just leaving. Thought he was going to close the door for me. Okay. So, this is just question 3. We'll do both A and B. We've been told that we have this. And we've been told that y is the sum from m equals 0 to infinity of a m x to the m plus r, for some r which we do not yet know. And then it says write down expressions for y dashed and y double dashed. Okay. So the am is a constant, so it'll stay there or multiplied by the current power, and the power will go down by 1. And if it didn't start with the plus r, I'd probably start it at 1 if I did that. But because m plus r minus 1 might be a proper power, I'll just keep it at 0. Okay. And then the y double dashed. The am will stay there because it's multiplied on. The m plus r will stay there because it's multiplied on. And the m plus r minus 1 will come down, and then the power will go down by another 1. And so they're my derivatives. So part A was fairly easy, so that's good. And then what you're supposed to do is you're supposed to sub these into there. Now they've told me not to derive it, but I just thought it would be useful to do that bit, to just sort of point out how the process works and how being organised in the way you do it might actually help you to get the answer right. So don't do this bit in the exam. So the exam asked not to do this bit, but I'm going to do it anyway, just so that I can get a handle on how this works. So, which is not a good plan. If they ask you not to do something in the exam, just don't. If you're the sort of person who finishes your exam 20 minutes early, do whatever you want. But I always took the whole time to do an exam, so it's not worth doing that. So, substituting equation 3 and its derivatives into equation 2, and rearranging some terms and shifting some indices, yields this intermediate result. Okay, I do want to do this though. So let's see. I've got x times y double dashed, and I've got minus 2x minus 1 times y dashed, and I've got x minus 2 times y. And all of those things have to add together to give 0. And personally, I find it easier to separately figure out what all of those things are, okay, before I add them together. So x, y double dashed would be, I would times this by x, so the power would go up by 1. Okay, that's my first one. And I'm just going to leave some space in case I have to shift some indices later. I'm going to need up here a minus 2x minus 1 lots of y dashed. I'm going to deal with the minus 2x and the plus 2 separately. So just let me expand that out first. So minus 2x minus 1 is minus 2x plus 2. Okay, so minus 2x times y dashed. Well, y dashed is this. Minus 1. If I times it by x, that minus 1 will go up 1. And I've got to times it by minus 2 as well. And 2y dashed is... need to leave myself space in case I have to shift. I didn't leave myself space. Sorry guys, it's going to get bad. Okay, and then the last thing I have is x minus 2y in the original formula. So I'm going to have x lots of y. So the power will go up by 1. And I'm just going to have minus 2y Okay, so I have all of these pieces, and if I add them all together, it's supposed to come out to 0. It's supposed to have x y double dashed, minus 2xy dashed, 2y dashed, xy, and minus 2y. If I add them all together, it's supposed to come out to 0. But I can't add them all together because in my sums, the powers don't match. So I need to make the powers match so that I can add these sums together properly. Okay, so why is there a plus 1 there? Alright, I maybe have done something wrong already, but I'm fairly sure I haven't. Okay, so how am I going to make this work? You need to deal with the powers before you deal with the where they start. So, okay. Does it bother anyone else that this has a plus 1 here? I probably shouldn't get ahead of myself. So how would I do that? This has got an n plus r minus 1, this has got an n plus r, this has got an n plus r minus 1, this has got an n plus r plus 1, this has got an n plus 1, n plus r. So I need to sort of shift my m's over so that they all match, and usually you make them all match the biggest one, right? Doesn't matter, pick one. Doesn't matter, you just pick whichever one you want. Okay, n plus r sounds nice and simple, so I might run with that. So this one's good, this one's good. I'm going to have to shift this one forwards and shift this one back. You probably should do whichever one requires the least amount of shifting. So if I want to shift this one forwards, I'm going to have to add 1 to the m, which means I'm going to have to subtract 1 to these. So add 1 to all the m's here and subtract 1 from them there. I think I see where things might be coming from. So cursors, I have to write it all out in full, but I might as well put it next to this one so I can see. So, I need this to go up to m plus r. I think traditionally you actually usually go up to the biggest one, but this will do. So I need to add 1 to my m, I need to add 1 to all the m's and subtract 1 from that one. So this will actually start at minus 1. Okay, so everything's gone up by 1. So this m plus r minus 1 has gone up by 1 because the m has gone up by 1. Okay, so now that's great. my minus 2xy dashed is fine. My 2y dash needs to be shifted forwards as well.
Could you shift the notes to the side?
Thank you, sorry. So I had this one, and that has to be shifted forward, so I can add 1 to all of them and subtract 1 there. Alright, and the xy was too high. It was at r plus 1, so I'm going to have to shift that back. So I subtract 1 from the m's and add 1 to this, because infinity plus 1 is still 1. And then my other one was still okay. Okay. Sorry, I can't fit them all on the screen. I could go out a little bit. Okay, so that's what I've got now, and now all the powers match. But they don't all start at the same place. So normally what you do after that is try and make them all start at the same place. Now what your lecturer has done in this question, not your lecturer, but whoever was lecturing in 2011, what they did in this question in the exam is that they've added them together in a certain way that requires you on paper to still shift one of the indices. And so that's sad, really. So the next stage would be to try and make make the beginnings match by just pulling out the first few terms. So, excuse me. So we know that when m is minus 1, that's the smallest power, and m equals 0 is the next power, and then they all do have a 1 in them, and so that's how you'll get your various things. So I'm not going to quite do what they've asked you in the exam, but we know that the smallest m is minus 1, and so I'll look at what happens when m is minus 1. And so when m is minus 1, I get a minus 1 plus 1, so that's what from the xy double dash term, I've got a minus 1 plus 1, minus 1 plus 1 plus r, minus 1 plus r, x to the minus 1 plus r. Not that it matters, but it's important to have that, just for my own sanity. And this one's got a minus 1 as well. This one doesn't have any, this one doesn't have any, this one doesn't have any one. And so the other one with the minus 1 is this one, plus 2, a minus 1 plus 1, minus 1 plus 1 plus r, x to the minus 1 plus r. Cool, and so they have the same power, which is the whole point of this. And so this is my coefficient, okay? So that's my coefficient. It's equal to this, which is a0 r minus 1 plus 2 a0 r, which is a0r outside of r minus 1 plus 2, which is r plus 1. And we know that because when I sub all of these, add all these together, they all have to come up to 0. So if I add all these together, the sum of these equals 0. That means that every single coefficient has to be 0, and so therefore this is 0. And so my initial equation is the r plus 1 equals 0. And so that's telling me that in fact either r is 0 or r is minus 1. Okay, that's how you get the initial equation. Back here, he's given us a particular thing, and we would have had to shift this one forwards so that it matches with these powers, and then that would give me an m equals minus 1 that I can sub in to find the initial equation. Okay. And then, to get your recurrence relation, you first have to pick one of the r's so that you can sub it in to get power series that work for you. So if this was an ordinary power series question, there wouldn't be an r and we wouldn't have to figure out what it is. But for this one we do. So if r equals 0, which is what they told me to do in the exam, and my experience tells me that they will always tell you one of the r's. And that's my experience from looking through the exams, but they'll always tell you which r to do when, so it's probably not worth learning how to make the decision of which one. Apparently you try them both if you're doing this in reality. I don't know if anyone ever does this in reality, I'm not sure. Mathematicians, when they're coming up with new maths, have to do this sort of thing. So we go back to our equations that we had and we sub in r equals 0. So if r equals 0, we've got x, y double dashed. So my 2y dashed was my xy was and my minus 2y was okay. Alright, so the next stage is it says find in the exam question, find the expression for A1 in terms of A0 and write down the recurrence relation. So we've done m equals minus 1 already, and we did that back there, and that told us what R was. And the next, if you look at this one starts at minus 1, it goes minus 1, 0, and then 1. This one starts at 0, so it goes 0 and then 1. This one starts at 1, that's a plus 1. No, that was minus 1 as well. This one starts at minus 1, this one starts at 1, this one starts at 0. So just to remind myself what's going on here. Okay. So the first few where they don't match, we need to focus on them separately. So we've already dealt with the minus 1s. Okay. The next is to deal with the zeros. So this one doesn't have a 0 in it, so that's not going to come into it. But when m equals 0, maybe not with a box around it, but anyway, it doesn't matter. When m equals 0, that's this one, this one, this one, and this one. So when m equals 0, we've got a 0 plus 1, 0 plus 1, 0, x to the 0. Alright, so that one's gone. This one, when m equals 0, I've got minus 2, a 0, 0, x to the 0. Okay, so that one's gone. When m equals 0 for this one, I've got 2a1, 1, x to the 0. And then this one doesn't have a 0. And this one I've got minus 2a, 0, x to the 0. Now they all have an x to the 0, so it's not actually necessary to put that in, but it just helps me to focus when I'm doing this, so I can rub them out if I want. Now. So we end up with 2a1, so that's 0, 2a1 minus 2a0, and that's supposed to come out to 0 as well. Because any combination of coefficients from all of these together must come to 0 because the whole thing is 0. And so I'm going to get that A0 is the same, A1 is the same as A0. But sometimes you get A1 is like 2A0 or something like that, or 3. Okay. And now, so that gives you your initial condition that says that A1 and A0 are the same. And then from the M, just for M equals M, you know, M is greater than or equal to 1, then we can use that to do our recurrence relation. So just to be sure, I've got the 0, we did all the zeros, and now they all start at 1, and so I'm good. I can now just add them together as they are presented on the page. So now I have A, M plus 1, M plus 1, M plus, well, minus 2A, M plus 2A, M plus 1, M plus 1, plus A, M minus 1, minus 2A, M is 0. Okay, I'm just taking all of the bits without the x to the m's in them. And presumably I can rearrange this to figure out what M1 is in terms of the lower powers, M plus 1. So you get the biggest power equals in terms of the smaller, not powers, the biggest value of M compared to the others. So let's combine the M plus 1. So this has got the M plus 1s in it. So we've got A M plus 1 with an M plus 1. And left over we have an M and a 2. So that was from those two. And the AMs we can combine together. So we've got minus 2AM M plus 1. And then we've got plus 2A, no. Then we've just got plus AM minus 1. Cool. So I've got that A M plus 1, M plus 1, M plus 2 is 2AM M plus 1 minus AM minus 1. Cool. I don't do the division yet. And so therefore AM plus 1 is 2AM M plus 1 minus AM minus 1 over M plus 1 M plus 2. That's my recurrence relation. Oh, good. You get to write an exam book, so you can take as much space as you want. Okay, that's good. I was going, gosh, this took me 5 pages. So I just wanted to make sure they just didn't give you a space to write in. You are always allowed to ask for more exam books if you need them. So do remember that, and don't be embarrassed. You're also allowed to ask for more scribble paper. So, yes. Okay. And that's how to make a recurrence relation. And then the next question was, calculate the first 3 terms. Okay. So just to be sure of how to use this recurrence relation, using the recurrence relation, A0 is A0, because that's what we started. A1 is also A0. A2, according to the recurrence relation, A2 happens when M is 1. And so that would be M equals 1. So A2 would be 2A1 times 2 minus A0 over 1 plus 1, which is 2 times 3. Yep. But A1 is 0, so we've got 4A0 minus A0 over 6, which is 3A0 over 6, which is A0 over 2. And then you can continue in that way. They only asked me for the first 3, but just so that you can see how this works, A3, which happens when M is 2, I can go that it's 2 lots of A 2 plus 1 minus A 1 over 2 plus 1, 2 plus 2. So I've got 6A2 minus A1 over 3 times 6 over 12. But A2 was A0 on 2, and A1 was A0. So I've now got 3A0 minus A0, which is 2A0 over 12, which is A0 over 6. So I can calculate them all in terms of A0 if I want. And so therefore, I'm going to get that my y is A0 plus A1x plus A2x squared plus A3x cubed plus and so on. And this is actually A0, and A1 is A0, and A2 was A0 on 2, and A3 was A0 on 6. And it looks remarkably like that's going to be A0 times e to the x by the look of it. I can't be sure, but I'm fairly sure. Because so far we've got divided by 0 factorial, divided by 1 factorial, divided by 2 factorial, divided by 3 factorial. I can't be sure until I do a few more. So far this is the same as what we would have gotten if we had A0 times e to the x. So, yes. But that's all they ask. And presumably, the other value of r would give you a second solution, and then you'd have this one plus that one would give you all the solutions, and you've got your two. Normally how you've got two unknowns when you solve a second order differential equation. So the other value of r would give you the other one of these, and it would have its own A0, and it would all work out nicely. Okay, but my understanding from past exam papers is they don't usually get you to do both. Right. Feeling better about your power series at all? I hope no, not at all. Some things that I do to make my power series easier to cope with. Is this thing. I don't like writing it as sideways with like pluses because I can't see how everything lines up. If I just do all of them separately and split up all the polynomials into their separate pieces, then it's easier for me to keep track of what's going on. And I know that it sounds like you end up with a lot of writing, but I don't think it's any more writing than you would do otherwise. And for me personally, it helps me to focus and not get it wrong. And so a sacrifice of slightly more writing for getting it right is, I think, not too bad a sacrifice. Anyone got any questions about what I did there? Yep.
When you added the m equals -1 to get the indicial equation, could you add a different m to get a different indicial? You use the smallest m. Okay.
So, well, as you know, I haven't studied this myself, so I don't know all the possibilities, but my understanding is you find the smallest m that appears here, and you use that one to get the initial equation. Because if you use any of the others, you'll get two different a's. This one all had A0s, but if you use any of the others, you'll get like A1s and stuff. Yep.
I think you're supposed to take whatever ends up giving you the A or coefficient. Okay. And then, because you have to force that not to be equal to 0, and then that gives you your initial equation, I think.
Oh yeah, that'll work. So whichever one gives you A0, which is the first one anyway, usually. That sounds reasonable to me. My instinct from this, that has worked every time so far, is to use the smallest m that appears in your thing. But that reasoning that's made sense there is that your A0, it's going to have A0 and then A0 on 6 and stuff like that, and so you can't have the A0 being 0. And so you find ones that only include A0 if you can. Right. So you could have chosen a different m, but I think it would have had A1s and A0s wrapped up in it, and that wouldn't help.
Okay.
You
Yeah.
already said this is not asked in the exam. Up to what part was it?
Okay, so the bit that was in the... So let me actually do the exam question, because I wanted to do a whole thing. So, all right, actual exam question. So in an effort to be helpful, the lecturer who wrote this exam question has deliberately done some of the work for you. And the actual exam question, starting from part B, said, rearranging some terms and shifting some indices gives me this. Okay? And they told you not to derive it, and I personally did not actually derive that result at all, because I didn't do that. If I start from here, I can show you how to do it from there. Okay? So I was given m equals 0, am, m plus r minus 1 plus 1, x to the m plus r minus 1. And he did give, yeah. And I'll just leave some space underneath that one. And m equals 0 to infinity minus. So what I'm doing is I'm bringing the minus 2 inside, because it's easier for me to remember how that works if I bring it in. And minus 2 am m plus r plus 1 x to the m plus r. And m equals 1 to infinity am minus 1 x to the m plus r. And the sum of those three pieces is 0. That's what we were told in the exam. Okay? So this is going from literally what they were given in the exam. So knowing that I should be doing some sort of working to make the powers match, and knowing that I'm going to sub in a value of m in order to figure out your initial equation, I need to look at this and say, well, if I was faced with this halfway down my working, what would I do? Well, what I would do is I would make the powers match. So I'm just going to shift this one over. So I need it to be m plus r like the others, so I need to add 1 to this, which means I need to subtract 1 from this. Okay. And then I know that the sum of those three is 0, right? Together, it's equal to 0. And so now, it's similar to what I had before, but with different formulas, but it's okay. I'm going to choose the smallest m, which is minus 1 now. And sub that into this one. A minus 1 plus 1 is 0. Minus 1 plus 1 is 0. Minus 1 plus 2 is 1. And that would be x to the minus 1 plus r. That's the only term that has an m minus 1 in it, so I don't need that term. And that coefficient must be 0, and so I get that r is 0 or r is minus 1. So he's tried to be helpful by doing some of the algebra for you to get to this stage here. But it's the same reasoning as the other one. Once you've got a sum of a whole lot of sums, you've got sums all added together, you can, once they're all matching powers, then you can sub in the smallest power of m and get your initial equation. And then the next smallest m is 0. And if I sub in m equals 0, these two here have 0 as one of the options. This one doesn't have 0 as an option. So I've got a 0 plus 1 is 1, 0 plus 1 plus r. Oh no, we know what r is. Okay, you've got to pick the r before you do anything else. But I could sub it in, right? So r is 0. So m is 0 and r is 0, so we get 0 for that one. And we can ignore that. Oh, crap, I've done the wrong one. Gone too far. M is 0 and r is 0, so that's a 1. M is 0 and r is 0, so that's a 2. And then for the next one that involves 0, I've got minus 2a, 0, m is 0 and r is 0, so that's a 1. And I get that. And that's supposed to be equal to 0. So I've got 2a1 minus 2a0 equals 0, and so therefore a1 equals a0. So it's exactly the same as what I got last time, but I'm just taking it from the sums that I was given. Possibly to help myself focus, so I would have just put a box around that so it's easier to see. And then the same deal is, well, all the other values of m are shared by all three of these sums. They all have a 1 in them, so I can start with that. So I can now go m is greater than or equal to 1. And look at my formulas and just copy down what I had. am plus 1, m plus r plus 1, except r is 0. And sub in r equals 0. So that's this formula here. So that's that coefficient. Higher up I've got minus 2am m plus 1 because r is 0. And I've got am minus 1. And that's all equal to 0. And so I should be able to rearrange that to get am plus 1, m plus 1, m plus 2 equals 2am m plus 1 minus am minus 1. So am plus 1 is 2am m plus 1 minus am minus 1 over m plus 1 m plus 2. Which is the same as the one I got before, hopefully. Totally is. Awesome. Okay. So I was just working, in the other one, I was working from the ones that I had made personally. In this one, in the actual exam question, I was working from the sums that I had been given, and I found it helpful again to write them all out separately so that I could shift the indices and all of that sort of thing.
In your exam, was it specified to r equals 0?
It was, yes. So in the exam, they specified to do r equals 0. If they didn't specify, you would have to separately go r equals 0, this working, r equals minus 1, this working, and do them separately.
And then you just write them together in the end?
Yeah. So if I was doing this without specifying that r equals 0 as it did in the exam, I would have now gone, now what would have happened if r is minus 1? Which is what happens at this point. So I would have gone r equals minus 1, I would have gone separate working, and I would have got a different recurrence relation, and I would have gotten a different final answer for y. And then I would have just added them together, and that would have been the answer.
Yeah, those in superposition.
Sorry?
Those in superposition.
If that's the word for what that is, then yes. Okay. So you said superposition. I'm presuming that means, well, I don't know what it means. Differentiation is a linear operator, and so therefore any solutions you get to a differential equation you can add together and it will still be a solution. So, yeah, that's my understanding of it, but I understand it from a linear algebra point of view because that's my research area. Okay, couple of points how the Frobenius method is different from ordinary power series. If I had an ordinary power series, I wouldn't get this r equals 0, r equals 1 sort of thing. I would end up having both, like the A0 and the A1, I wouldn't be able to figure them both out. I wouldn't be able to figure out one in terms of the other. I'd just have them both separately, and I'd end up with two unknowns, an A0 and an A1, or an A0 and an A2 or something. You'd be able to write all the other ones in terms of two of them rather than in terms of one of them, and that's where your two solutions come from. Okay, so normally what you actually do is you pull out the A0 out of its bit, and the A 1 out of its bit, and there's your two solutions. So would anyone interested in me doing something else? Yep?
Question 6 from 2010.
Okay. (2010), question 6. Aha! I was hoping someone would ask for one of these. So this is your separation of variables, right? This one's a bit different to the ones that's been in your assignment. Okay. So we're given this differential equation. It's a partial differential equation. And we've got that the temperature is 0 at x equals 0, and the rod is insulated at the other end. And therefore the boundary conditions are and also the initial conditions are okay. Right. Good old separation of variables. Okay, so the exam question specifically says use separation of variables to solve that equation, subject to the boundary conditions and the initial condition. And they're using you may use the result that eigenvalues of blah blah blah, and we'll get to that. Okay. So my understanding of separation of variables goes like this. They normally use F and G. Some lecturers use capital X and capital T. What does your lecturer do? Sorry, F and G? Cool. Sorry, no? They use capital X and capital T, do they? Cothers. Well, doesn't really matter, but I would like to use what's most familiar with you, but this is the most familiar to me. So, okay, I'll use this if you don't mind. So, right. The whole purpose of this is to try and figure out separately what the F and G are, and then later on multiply them together to give U. Problem's going to happen is I'm going to get a whole sequence of possible F's and a whole sequence of possible G's, and I'm actually going to get an infinite series of F's times G's to make my U. So that's what's going to happen eventually. And it so happens that it's common enough in real world situations and in exam questions that there's a trig thing here, and so it's likely that you'll get some sort of Fourier series. Okay, it's likely that the infinite series that you get will involve sines and or causes, and therefore it's a Fourier series. So that's what we're really interested in here, making a Fourier series. Right. So there are two considerations, but before we get to them, we're going to have to differentiate this so that we can sub it in there. This is substitution. So I need to know what du on dt is and what d squared u on dx is. So if I differentiate this with respect to t, that f of x counts as a constant because it doesn't have a t in it, and so I'm going to have that will still be there because it's a constant and it's multiplied on, and then the g will get differentiated. I shall use a dot because it's tradition for derivatives with respect to time to be dots. And that's what's in the textbook. So, When I looked this up in the textbook, they use dots for derivatives with respect to time and dashes for derivatives with respect to x. You can use whatever you like, but this is how I learned it. I also need to know the second derivative of u with respect to x. So if I differentiate this with respect to x, the g this time will count as a constant because it doesn't involve any x's, and so it'll still be there when I differentiate because it's multiplied on, and the f will get differentiated twice, so I'll get this. Like that. Awesome. And then I sub them into the original formula. Okay, so I'm seeing ahead. I can see why they've only given me one of these. Normally you get two of these with the functions, but there's only one because this is only first order on this side. So I only need one. That's just getting ahead of myself. So normally this has got a second derivative as well. So they've deliberately made it easier by making it a first derivative. So we're just going to take it as read though. And so now we've got the du on dt and we've got the d squared u on dx squared, and we're going to sub them both into here. So sub into the differential equation. So the du on dt is fx g dashed x, and the d squared u on dx squared is f double dash x gt. And then we do this nice trick where we get all the x's and put them on one side and all the g's and put them on the other side. And it seems traditional to put your derivatives on the top. Not that it matters, but that's the tradition. So I can bring that down there and that down there, and then I have this. And here's the reasoning that goes that this here doesn't involve any x's, and this here doesn't involve any t's. And so since they're equal to each other, the function that they're both equal to doesn't involve any x's and it doesn't involve any t's either, and therefore it must be a constant. And so this must be some sort of constant. Okay, so they're saying they're both equal to something, all right, because they're equal to each other. They're equal to something. The something that they're equal to can't be a function of x because of this, and it can't be a function of t because of this, so it must be a constant. And that is the lambda that they're referring to most of the time, but the lambda confuses me, so I call it k. Okay, and then what we do is we focus on each half of this separately. And to choose which half to do, you need to go back and look at your conditions. So there's two ways of dealing with this. So notice how one of those sets of conditions comes out to a number. This one here comes out to a number. And the other condition comes out to a function. So the one that comes out to a function, you want to do that one second. Okay, so just note for this one, we picked a particular value of t, and it gave me a function. So this one was pick t, gives me function. And this one was pick x, and it gives me number, right? Okay, so you want to deal with so we're going to deal with this separately. First, not necessarily first, but one of them we're going to deal with g dot t over gt is k. And the other one we're going to deal with is f double dash g x over fx is k. We're going to deal with both of them separately, and to decide which one to do first, we're going to go back here and do the one that comes to a number first. So we picked x and it gave me a number, so we focus on the x first. That's the reasoning behind this. Okay? Because it's much easier to deal with the number one. And if there were other numbers involved, so if my original one had like a 4 here, I would make sure that the one I did first, I would separate the 4 out and move it away from that part of it. So if I ended up with a 4 in this spot, I would move that 4 over to this side so that the first one I did didn't involve any other numbers. Okay, so that's the reasoning behind how to make that choice. So I'll focus on the x first. I think the reason it's written this way is that you can directly go from there to the answer in terms of some ways of doing it traditionally in the past. These days, we rearrange this like this. And we get that. Now, one of the nice things about this is that this is a second order differential equation. It has constant coefficients because k is just a number. And a second order differential equation with constant coefficients, we learned how to deal with them way back in Maths 1B. So we would normally do like a characteristic equation. So we've got second order constant coefficients, and we do a characteristic equation, and so we get lambda squared minus k equals 0. And then you'd explicitly try what would happen if the k was positive and if the k was negative and if the k was 0, and do all this stuff, but they've told me what the answer to that part of the question is. Okay, so and more working, which I may or may not show you if you're interested, but I'll do the actual exam question first. They've told me right here that if I saw an equation of y double dash minus lambda y equals 0, and I had the initial conditions that y of 0 is 0 and y dashed at pi on 2 is 0, well, let's compare that to what we've got. We've got our f double dashed x minus k of f of x is 0. That's exactly the same, except I've got capital F of x instead of y and k instead of lambda, so that's the same. And then when I come back to my initial conditions, when I sub in a value for x, the answer comes out to 0. When I sub in a value for x, the answer comes out to 0. When I differentiate it with respect to x and sub in the value of pi on 2, the answer comes to 0. When I differentiate the y with respect to x and sub in pi on 2, the answer comes out to 0. So this is the same as the situation we have up here with these initial conditions. And so therefore the solution must be that the k that I had is equal to this, and this is the solution. So I can go straight to writing that down. Whoa, back. So that means my f of x must be sine of 2n minus 1 x, and that's the nth x, and I also know that the k is minus 2n minus 1 squared for n equals 1, 2, 3, and so on. That's what they told me in the question that the answer to that particular part of my problem was. Okay. Cool. And so now I've got all these infinitely many possibilities for what f could be. Okay. But I do know what k is. So now I'm going to go back and focus on the t's now, because I haven't done that half of the original equation. So if I go back and focus on the t's in this equation here, I've got g dot t over gt is k. But I know that k, I was just told what k was. K is in fact this. Because I just figured out what k was. And so now, ignoring this bit in the middle, I can rearrange this to get g dot t in fact, I don't need to rearrange that. If I was doing a second order, no, I do. That's okay. I'll just put it back here like this. If this was a second order one, I'd bring what was there onto the other side, and I'd do my lambdas, and I'd get something. Okay, but this is first order. And it's actually first order separable, so I can actually separate it. But you know, hopefully you were taught that first order separable is actually the same as just doing characteristic equations anyway. Have you been taught that? I'll show you, it's really cool. Well, it's mildly cool. To me. Okay, so look at this. If I was going to turn this into a characteristic polynomial, this would be the constant term, the original function, and the first derivative would be lambda, and the second derivative would be lambda squared, and so on. And so I'm going to get lambda plus 2n minus 1 squared equals 0. And so lambda is minus 2n minus 1 squared. And then my solution would be e to the lambda x, well, e to the lambda t. Just the same as if I did it with a second order one, and I got two lambdas, and I would have e to the whatever t and e to the other t. Well, you can do it with the first order as well, rather than doing separable differential equations. It's actually really cool. Only works for constants, but it's nice when it is constant. And so I get that g of t is e to the minus 2n minus 1 squared t, with a constant out the front, right, of some sort. Okay. Now if I was doing a second order one, there would have been two constants, like an a and a b. Okay. Now this is the nth one though, because there's an n in this formula, it's gn. So now just to recap where I've been, so fn x was sine of 2n minus 1 x, and gn x is a e to the minus 2n minus 1 squared t. Okay, and u is the product of those. So un...
Should it be GNT?
Yeah, it totally should, thank you. Well done. And u is the product of those, so it'll be sine... It'll be that. And then u itself will be the sum of all of those. Okay, so u will be the infinite sum of all of those things. Now where did n start? Started at 1. Okay, so let's just recap where we've been here. We supposed that it was f of f times g. We differentiated as many times as we needed, and we subbed it into the original differential equation, and we got this. So that's sort of like part 1. Okay, so this is the very original part. And then we sub that in, so together that's sort of part 1. And then once we've got this equation, we look at each part separately, and we go, let's focus on the x's, and it gave us some solutions. And then the next part is to focus on the t's, and it gave us some solutions. And then finally we put those solutions together, and I've figured out what u is. Final step is to try and figure out what that a is. Only just a second. Each n might give me a different a. Okay, so now I need to figure out what those a's are. Okay, well let's just go back now. There's one piece of information we have not yet used. And it's there. U of x 0 is sine 3x. So that tells me when I sub t is equals 0 in, what the formula comes out to is sine 3x. So let's just look at that then. So I know that u of x 0 is sine 3x. So u of x0 will be what I get when I put t equals 0 in. And e to the 0 is 1. But just to make it explicit, so I get that. Nope, n equals 1, sorry. Too focused on my zeros. And this is supposed to be equal to sine 3x. Okay, so let's just start, I just want to start writing this down. Let's just actually put the first few terms down so that I can see what's going on. So when n equals 1, I get a1 sine 2 times 1 minus 1, which is 1x. And when n equals 2, I get a2 sine 2 times 2 minus 1, which is 3x. And when n equals 3, I get a3 sine 5x. And so on. And this is supposed to be equal to sine 3x. The only way that can possibly be equal to sine 3x is if that one is 1 and all these other ones are 0. Because then it would be equal to sine 3x, right? If they were 0 and that was 1, this would be equal to sine 3x. And so therefore, a2 equals 1 and an equals 0 for all other n. So those of you who are in the Maths Learning Centre during the throes of the final assignment would have remembered that, you know, we got, when n is 4, we got this one, when n is 9, we got this one, and when n is 16, we got this one, and we combined them together into the final answer. This one we only have to deal with one of them. And so therefore, just going back to subbing that in, since the only one that's not 0 is a2, back here in this sum, it's just the one where n is 2. So let's just think about this. So u is in fact only equal to the one where n is equal to 2, because all the other ones, the a is 0. So when n is 2, we've got the sum from, no, we don't have a sum anymore because we've only got n equals 2. We've got a2, which was 1, but just to put it in a second, sine 2 times 2 minus 1x, e to the minus 2 times 2 plus 1, is it a plus 1? It's a minus 1, sorry. Two times 2 minus 1 squared t. Okay, that's the only one that's not 0. And a2 is 1, so it's sine 3x e to the minus, now that's 3, 9t. And that is what u is. And now we have a solution. Right, that's separation of variables. Yay. Except for the bit where you had to solve this bit here. Now, have there been any exams where you expected to solve that? Anyone notice? Yes? Awesome. So why don't I just do that missing bit so that you can see where it came from? Now it's really common when lecturers do this for them to do part of it for you. Okay? So I've seen several exams where they do that bit for you. And I've seen other exams where they do a different bit for you. So we're going to do that missing part, which was to solve this. There was, I don't know if it was an exam question, there was one where it had a plus here, which stuffed us up a little, but you've got to be careful and look at what they've given you to make sure that you make it look the same as what they've got. Okay, but traditionally you put a minus there. Okay, so if this is second order constant coefficients, and so I'll go, my characteristic equation is lambda squared minus k equals 0, which gives me lambda squared is k, which would have different solutions depending on what k was. So if k was 0, the only solution would be lambda is 0. So we've got these three options. K equals 0, which would mean that lambda squared is 0, which means that lambda would be 0 and 0, which means that I would get that f would be e to the 0x and x e to the 0x. Because that's how you do it when you have a repeated root. So it would be a plus bx, something like that. That's what would happen if k is 0. I don't know if I'll have enough room to do all of these. If k is positive, yep. If k is positive, it might be something squared, which would be a nice way to do it. But if k was positive, I'm just going to write this bit in soft so you can see what's going to happen. I'd have lambda squared equals k, and that means that lambda would be plus or minus root k, right? So what I'm going to do, actually I'm just going to write it exactly like that. Lambda squared equals k. So lambda is plus or minus root k. And so I'll get e to the root k x and e to the minus root kx. But because I don't want to put roots everywhere, I'm going to give a name to root k so that I can do this properly. So I know they use traditional letters like p and mu and stuff. I don't know which one they use for which. Does anyone remember that deeply into these examples?
Why do they use mu or like the Greek V thing? Whatever.
Nu.
Yeah, that one.
Looks like a V. All right. Let's do it as mu. And so therefore we get that lambda is plus or minus mu, and we get therefore that f is a e to the mu x and b e to the minus mu x. Okay, I wouldn't normally do these across ways, but just I want you to see them all together. And then if k was negative, I get lambda squared equals k. But because k is negative, when I square root it, I'm going to get a plus or minus, I'm going to get an I. Okay? So knowing that it's negative, I'm going to do the same trick as I did here and suppose that k is like minus nu squared. Okay? That's totally doesn't look like a nu. Right. That difference is marginal, I know, but I feel better. So that's my lambda squared, and so my lambda will be plus or minus nu I. And so therefore, because this is 0 plus or minus nu I, when you do solving of linear constant coefficient differential equations, the correct response for this is f equals a e to the 0x cos nu x and b e to the 0x sine nu x. But because that's 0, e to the 0 is 1, so I can get this. And so we get all three of these possibilities, and each of them has infinitely many possibilities. So 3 times infinity. But it's a good thing that 3 times infinity is still infinity, so it doesn't get any worse. Yeah, that's a really bad dad joke, I'm sorry. A maths dad joke, the worst kind. So the next stage is that some of these, the only solution you actually get is when a and b are both 0, and that's not helpful. The function is the 0 function. Awesome, yay, nothing changes. So what you want to do is you want to look for possibilities where the a's and the b's aren't 0. So what's going to happen is I'm going to end up with my new, that new is where my solutions are going to come from. So I'm going to go, each of those separately I'm going to have to run through and see what happens to them. There was at least one exam where they specifically asked you to do just this bit and they did all the rest for you. So it's just good to know that you can do it. So if k equals 0, I get that f is a plus bx. And then I have to go back to those initial conditions, which were that so u of 0t was 0, which means that f of 0 is 0. Okay? And u sub x of pi on 2t was 0, which means that f dash pi on 2 is 0. So I need to figure out what these two things are. So f of 0 is a plus b times 0, which is 0, so therefore a is 0. And f dash x is b, and f dash pi on 2 is still b, which is supposed to be 0, so b is 0, and so therefore f is the 0 function. I use a triple equals because that means identically 0, meaning it's 0 for all possible x's. Just to point out that it's not one particular x I'm thinking about. And so this one didn't give me any solutions that weren't 0, so I can ignore that. When k was positive, I got that f was a e to the mu x plus b e to the minus mu x. And I know that f of 0 is 0, so that means that a e to the 0 plus b e to the 0 is 0, so a plus b is 0. And I also know that f dash to pi on 2 is 0, which means that I need to figure out what f dashed is. F dashed x is mu a e to the mu x minus mu b e to the mu x. And so f dash to pi on 2 is not pretty. Okay. All right. To make this easier on myself, I'm going to say that all of this is a number of some sort. So, for some a not equal to b, which are whatever those numbers are. So the only way that two numbers can do this is for them both to be 0. Because if I times this one by b, for example, I would get ba, and we can do this, times b. ba plus bb is 0, and then I can subtract these two, and I'll have b minus a is 0, which means that a has to be 0 because a was not equal to b. So it doesn't much matter what is here, as long as I can be certain that those two numbers are not equal to each other, I can be certain that a is not equal to b, that I get a equals 0, and subbing that back into this, I get b equals 0 as well. It is okay, back at this stage, to go, therefore a and b are both 0, without doing any more working. But that's the reasoning behind it. If I wanted to do it all properly, I would sort of times this one by mu e to the pi on 2 mu or something. And then I could subtract and stuff would happen. Okay, so therefore, again, f is identically equal to 0. And so I don't get any solutions there, well, no useful ones, I just get the 0 solution. And I knew that was a solution right from the beginning. And so finally, I deal with the case where k is negative, which got me the solution of f is a cos nu x plus b sine nu x. If you traditionally put a as the constant term and b as the coefficient of x, you should also put a for cos and b for sine, because cos is even and so is a constant, and sine is odd and so is x, and so you should make your letters match the odd functions and even functions. Just makes your working easier. If you don't remember to do that, it doesn't matter, but it's best to put a as the... If you use a and b for cos and sine, is to do it for constant and coefficient of x as well. Just if you've never noticed why that would be useful, then don't worry about it. It's just, I think it's useful. Okay, and so now I got my same deal. F of 0 is 0, so a cos of nu times 0 plus b sine of nu times 0 is 0. Now cos of 0 is 1, sine of 0 is 0, so a is 0. So that's awesome, and so therefore because a is 0, I can actually sub that back in here early because it's going to make my life easier. I could have actually just done it separate, but it's a really good plan to do it now. So therefore f is actually just b sine nu x. If you want to learn how to write a nu so it looks good, it's an n, but you start almost all the way to the top. It's a capital N like this. You start here. So you start here and go like that.
Thank you.
Oh, the capital nu is an N. Because the Greeks and the Romans, we got our alphabet from the Romans, and the Romans stole their alphabet from the Greeks, and at that stage they were all capital letters, but the small letters were developed independently. And so we thought that a small n should look like this, and they thought that a small n should look like that. So there you go. It's really, you learn something new every day, and it's usually not maths. So the next stage I had was that f dash to pi on 2 was also 0. So I need what f dash x is first, which is b cos nu x, but the nu will come out because it's a constant. And this is 0. Now, this has three possibilities. Either nu is 0, which isn't allowed, because we know that, that k wasn't 0, or b is 0, and that would give me that the only solution is that f is identically equal to 0 as well, and we've already covered that. And so we're going to say, well, we know that nu isn't 0. We're going to assume that b isn't 0. And so therefore cos of nu x, sorry, not yet, 1 second. F dash to pi on 2 is nu b cos of nu times pi on 2 equals 0. So that means, therefore, that cos of nu times pi on 2 is in fact 0. Now let's just think about cos. On my unit circle, cos is 0 here and here, which are the odd multiples of pi on 2. So nu has to be an odd integer. Okay, and the odd integers, well, they're 2n minus 1 for some n. So therefore, nu is 2n minus 1 for n equals 1, 2, etc. We don't have to worry about the negative ones because we're going to square it anyway, so we don't have to worry about that. Because remember the k was nu squared, so the negative ones don't matter. And so therefore, going back to what k was minus nu squared, which is minus 2n minus 1 squared, and fn was, now, what's my b? Oh, that's okay. No, just a second. And f was b sine 2n minus 1 x, Okay, but remember, we're going to get some arbitrary coefficients from the g's, so we don't have to put this one in. We get to choose any multiple of this and it's okay. So we choose a multiple and we choose the multiple 1. So first for some d, so choose fn to be sine of 2n minus 1x. Just like when you find eigenvectors way back in Maths 1a, you're allowed to choose any multiple of that eigenvector and it's okay. Same deal here. Eigenfunctions, you're allowed to choose any multiple of them. Right, that's how to do that part. And then you feed that into the second part and the rest of it follows. Well, you're supposed to be able to talk to your actual own lecturer now in his consulting time, as far as I'm aware. I think that's right. So I'm not going to steal you from him. All go at once to his office. That'd be really cool. Do be aware that I'd prefer you to sit next to and not in the Maths Learning Centre as we get closer to the exam. Your exam is the day before the first year maths exam, so it'll be extremely busy on the Maths Learning Centre on Monday. So we will try and commandeer the whole of that space for maths, and I'll make some space for you, okay? All right, thanks very much. Any more questions, do ask, but remember, not all of us are completely experienced with differential equations. So cut us some slack and give us some time and work with each other as much as you can. Thanks.